And around the solar arena, there's been a number of discussions. This one particularly.
Yeah, that's what I was going to try to sign in on here so I could admit him as the admin too, but I didn't know.
Hey, Ashley, I hear you.
Oh, I'm sorry. Sorry.
No problem at all. Well, and I actually told them, by the way, I'll just say, keep this fluid. You know, like if things come in as we're talking, I'm happy to do things on the fly. I don't need to give you guys a full presentation, but I have it and I've got some information to share. This one has resonated with people very much so, is what I will say. And I'll get into the discussion of it as we kind of step along here. But I really want to focus on this one at the distribution engineer level that many of you, I guess, obviously are very concerned about. I want to talk about the impact of, granted, you may have an individual commercial consumer bringing in a single larger system, or you may have a bunch of the little ones that are just flooding individual feeders. And the thrust of this discussion is to, I always say it this way, I want to make your eyes wide open for what the impact is on your distribution systems, because many people are not fully aware of what's happening by allowing these things. I know, you know, when I was there at the co-op, I was permitting these things like crazy. I was getting calls every week, and I know many of you were, and it may have slowed down with the funding cycle lapse, but it has continued, and we know that because we're helping clients study their systems for it. And so the question is, what is that doing, and what have you looked at with your system protection schemes and such to mitigate? Now, Finley, many of you know Finley, or if you're not aware, Finley's been in business since the 50s, both electric and telecom. Most people know them more from their telecom connectivity. If you ask a telephone co-op, they all know who Finley is, but a lot of electric co-ops I found don't. But we do everything, and we have the synergy of the two, which has been a neat fit for me and my help with it. So we're all over the Midwest. I'm at our office in Springfield, Illinois here, and that's how we help people with anything they've got, consulting. So let's talk a little about distributed generation just a bit. The market, this isn't anything that people wouldn't imagine to be true. You look at where it's at today and where it's growing to from anything, mostly solar, we know that, but other things going on the market, it's just amazing when you look at the statistics. And this is when I looked it up. It's even higher than this now. But the market's not quitting, it's not going away. That's the story of that slide. And you know, kind of the same thing here, just talking about the growth rates, and we're seeing more, not just the individual residentials, the 10 kW size units, but we're seeing more of the small hog confinement operators and other. We just had a seed business doing one of my clients, and doing the several hundred kW size systems, up to the 0.5 megawatt or megawatt size systems. And the question is, what do you do with your system, and what's that going to mean? That's what I'm trying to bring up to you. That's what I want to bring to your attention, and we'll just kind of step through. I want to bring some of where we're at, and then use that to step forward into where we should be. So I'll give you that quick synopsis, if you will. Where are we at today? You know, when I survey individual co-ops, let's say this average size, kind of where we were, many will tell this story right here. That, yeah, they may or may not have a few smart breakers. They're typically at the substation. If this resonates with you, you can just nod silently in agreement. Most of them are the good old-fashioned hydraulic reclosers downstream. And we typically use these rules of thumb standards like the 1A, 3C at the sub and a 2A, 2B, and we do a coordination. A lot of typical feeders are, if they're the sub breakers, there's 1, 2, maybe even 3 if it's a long feeder, midstream coordination points. So again, that's what I see. You can see if that resonates with you, but that's what, you know, surveying like all over the Midwest and even the South, that tends to be the case. What's the load look like? Very typically, it has been characteristically good old-fashioned inductive resistive loading. And that's our makeup of things. Now, there are more nonlinear and other sources starting to come online, and that's going to be one of the thrusts of this discussion, of course. But it has still been typically most of what we see. And here's another one. What kind of fault currents? You know, you survey the average size co-op, 10 MVA is pretty typical and less. We had a lot of 2.5s and 3.75s, 5s. But that's pretty typical, unless you have a dedicated customer with a express feeder, where you might have a bigger size transformer. But that puts you in that magnitude fault current. We're going to talk a lot about fault current in this discussion because it's critical to what I'm trying to bring up. But you see it bounded by those ranges by that size of transformer. And you know, those that have looked at a light table graph and tried to coordinate, you know, your typical hydraulics, you're fairly limited. You've got those ABC curves, and you can try to plot those against each other and see where things fall. And now with the advent of our smart breakers, obviously being able to pick the curves, we can do a much better job of coordination. We've got more things to coordinate. If you're trying to think about the high sides in addition to your scheme and what you've got going on downstream and customer impact, you need the flexibility, and that's why we're seeing more of these at the subs, I guess, just to have that flexibility. Also, when you look at a traditional coordination, very typical, you've got a load current, and when we have a fault event, we're having some series of either fast operation to clear the temporary faults or the slow operations to get the rest and trying to clear. This is going to be important. I don't need to give you a lesson in engineering and for distribution engineering, but it's important because I'm going to come back to this point, which is you see the coordination intervals and how we're used to doing things. Typical loads, typical fault currents, typical coordinations. Okay, this is an interesting point to bring up that I just kind of want to note. And it's funny, I've brought this topic up to some places that don't know the term, but I knew this very well. I remember as a young pup engineer right out of school, and I was having a discussion with some linemen after some outage event we had. And they talked about having some run throughs. And I was like, that didn't sound like something I learned in college. So I said, what's a run through? What do you mean? And they said, oh, well, sometimes when you have a fault, the breaker that's closest to the fault trips and clears the fault. Sometimes it doesn't. Like, what do you mean sometimes it doesn't? That doesn't sound like a proper way to engineer a system. But they said, oh, well, it just depends on the fault. But sometimes it gets that breaker, sometimes it gets one upstream, or sometimes it gets the sub. And I scratched my head and I said, that doesn't sound like something that should be right. Well, what did I find out? This, that if you don't look at the parameters on these things, the actual loading ratings on these devices, you may have one in the wrong spot. For instance, I found a number of these where I got not a mile out of the sub and they were using an H35 or something like that. And I looked up the fault current available at that site and it should have been a 4H. Well, it couldn't handle the capacity. So what was the reality? And this will be important as I talk about this impact, because we know there's a minimum fault current threshold, there's regular fault current availability at that site. But depending on that magnitude, we all know not all faults are the same. One fault may generate a little bit of fault current, minimal. Others may generate both of the fault current. And those ones with a higher magnitude, of course, given the conditions, created a different impact on the system. I thought that was just very intriguing and definitely one that if you weren't aware, you had to kind of be mindful of. And so it's amazing in the co-op world, and unis do the same thing, just so you know, that I've learned here since being at Finley. IOUs tend to maybe do it a little different in some cases, but everybody likes rules of thumb. And they do work. They've worked for decades, frankly. But here's an interesting statistic if you look at this. The reason we tend to skip sizes, like we go L100s at the sub, and then maybe we jump from 70s to 50s, and then we jump maybe to 25s, it's because skipping sizes ensures non-simultaneous operations with standard devices. Because you get too close, anything less than 2 cycles is going to be simultaneous. A lot of people don't necessarily realize that, but that's why that's there, and anybody that does the time studying obviously knows that. But this is it's why it works when we do skip and we have these rules. Obviously, with today, we've got the potential for faster tripping and ground fault tripping, other things that we've got to do to meet our RS requirements and things like that. Triple single was a wonderful advent, of course, with that wrong. I just bring that up because of where we're able to do a much better job of coordinating. We can dovetail those faster curves in with our traditionals to come up with an improved result. Now, when I mentioned my whole thing about faults not being created equal, this is just an interesting statistic. You pretty much know most of our faults are unsymmetrical. They're aligned to ground. Look at that, 65 to 70%. But your symmetrical are your more damaging faults because they generate more fault current. I mean, we don't have that happen too often unless the whole thing comes down. It all gets together at once, line to line to line to ground or something like that. I mean, the guy that was trying to steal copper years ago that would throw the chain up there and get it all at once, yeah, he was causing us some issues. But Otherwise, we're kind of in these frameworks for faults, but we know they're not the same. It depends on what they're going through. And we know it's dictated by that. I always remember in school, that was one of those pieces that they would teach you the ideal circuit. And I remember thinking, what's the point of learning the ideal circuit if that doesn't exist in real life? Well, it's so we know what could be available. But in reality, the impedance is going to change that. So we're not going to have full infinite fault current. We have a multiple of rated current, somewhere in the 5, 10, maybe 20 times, 30 times, depending on how efficient your transformer and facilities are, and how long those copper lines are going out to the surface. This is just another interesting point that a lot of people don't grasp. What is the point of our protection in general? Well, we want to generate massive fault current quickly to trip protected devices. That's protecting the public. And so we want to isolate as fast as we can and segment as much as we can to limit the impact, of course, and that impacts our safety, all those wonderful metrics. And everything connected along the way is going to change that parameter for us. So enter the picture. Now we're putting solar and other entities like it on our systems, and they have a nonlinear interconnecting source. They're an inverter source. They're not a rotating induction device. We've got power electronics that is bringing this to the grid, and it's coming on our system. So what does that do? What are we trying to be mindful of? What are we being concerned about? Okay, I'm going to point out some standards here because it's instructive for the discussion. That may be a little small to zoom in, but IEEE obviously is taking the lead, and the UL has the listing agency for coming up with the products and devices and certifying them. I always have when we permit these systems coming on, we want to see their UL cert, of course. But what's interesting is if you look at the standards, the 03 standard for 1547 said that they shall not actively regulate voltage and shall trip on abnormal voltage frequency. By the time the 14 standard came around, it was may actively regulate. Well, then by the 18 standard, it says shall be capable of actively regulating. What's this mean to you as the operator? Manufacturers are building devices to hang on. We're going to talk about fault ride theory here in just a few minutes because this is important to our discussion. Devices that used to trip quickly due to a fault occurrence are now trying to hang on because of power electronics. I've gotten so much better capacity and magnitude capability. They can hang on through a temporary and some faults and contribute to your fault total current. So I'm going to come back to that discussion. Keep that in mind. We'll bring this back up. Also on voltage regulation, the ANSI standards. This is an interesting point because bringing a source generation piece onto your feeder at some point in the segment can impact what ultimately happens. Now, I won't just be talking mindlessly. Let's bring in some discussions. Okay, so here I have an example for you. And we're going to talk about voltage regulation first. We'll come back to system protection. So you look at this example, and here at the top, I've got a typical feed, and you got the substation. And in this example, we're injecting a PV source close to the substation. So if you look at my graph here, I'm showing the ANSI lower limit. I mean, typically the ANSI is like 108 to 126. That's what we use to carry our substations, knowing we got to compensate for getting all the way out to the end of the feeder with adequate voltage. Maybe you've got midstream regulation, whatever. But let's say in this model, we've got substation regulation. And if you see the black curve there, we got a typical profile. You've ramped it up to something high enough at the sub that the tail end, you're still meeting standards, and you're fine. But with an injected source close to the substation, you have the potential for, and read my figure there, you got the note, line drop compensation can get confused with that depending on how they're set, where that regulator may not step because of the injected source, but you could end up with tail regulation concerns. I think that's an interesting one. People may not realize that's happening if you're not out there reading that. So let's do the inverse of this same discussion now, and let's inject the PV source at the end of the feed. So look at the potential. I've shown you both in red, the upper and lower limits there. We can see the 108 to 126. And in red, you're seeing what would have been the normal profile. But look at the potential for in-line voltage elevation due to a source and this regulator possibly stepping down or not stepping due to its impact and you could end up with a tail out of zone regulation voltage issue. Like I said, this one's just to kind of, usually it's an eye opener with people that they don't even realize this potential can exist. Especially then you've got multiple sets of coordination between different sets of regulation, could be exacerbated by that potential. So I'm just bringing up some of these. We're going to talk about mitigations here toward the end. It's an interesting point. So now let's talk a little bit about fault current on that side. What is the impact and what is it doing to the system? And I'm going to give you some examples. It's always better to see an example and know what I'm talking about. And a couple of these things, nuisance and sympathetic tripping, are interesting topics that a lot of people may not be aware of. But we do know, I made that point, that your traditional OCR is not a directional sensing device. It's not a smart control on that thing. So let's use one example. What we consider an underreach of your coordination. So in my example A, if you see here, we got breaker B and PV system noted. Now, if we show the fault at where I've got the nice little lightning bolt, and normal fault current magnitude would be in blue, so you'd see fault current through breaker B feeding into the fault, I fault that I'm calling there next figure A, and look at the typical coordination in blue over on the graph, or purple, it's kind of. You see that Reclosers' ability to coordinate, and that fault current and its time to trip, and its ability to stay in coordination with the downstream regulator. Now notice what could happen in this potential. And I'm noting in figure A there, an example of an underreach is the PV system, due to its ability to feed into the fault quickly before its protection scheme may enact, it's going to feed into that fault potentially, and it may not draw the same magnitude fault current through breaker B, basically meaning breaker B may not trip in a certain fault condition. We call that an underreach because it's not protecting in that case. If you have a low level magnitude fault, you have the potential that the breaker B won't trip. And then you can see it from the curves there. Look at the potential, or you're going to go upstream and you're going to trip on a faster curve, or something that can handle a higher magnitude. And you can see the change in threshold current or the time to trip. That one's kind of an interesting one. A lot of people don't necessarily realize that potential exists.
Hey, Sean, you have a quick question. What was the third difference between the original IEEE code and today's?
This one? Is that the one we're talking about? I'd say so. Okay, the 18 standard came out and has said that a distributed generation system shall be capable of actively regulating voltage and shall ride through abnormal voltage frequency and frequency response. That's the three parameters they have talked about or added. So as of the 18 standard, now granted, a bolted fault is still going to make the inverter trip out. But the 18 standard is written so that the manufacturers producing products to meet the 1547 2018 version standard are trying to build the power electronics in such a way that they will ride through minimum level faults and try to actively regulate to hang on, if you will. That's the best analogy to do it. Again, if you got a bolted fault to ground, this thing's going to operate, it should come off, and your devices should trip like normal. But there are low-level magnitude faults or others that are less than so many cycles or whatever the parameters that are built into that. I don't have the statistic off the top of my head that actually gives the per cycle variation there. But the point is they are building them to do that and be more. I'm going to actually come back to that point here in a little bit because I'm going to talk about why they did it. Because you might be scratching your head saying, why would they do that? And here's the quick difference. You are operating a distribution system and you want these things tripping off because, like we said, you're protecting the public and you want these things coming off the grid to isolate and minimize fault. But a regional operator does not want big multi-megawatt solar farms coming off grid at the same time. And they have better lobbying ability than you and I do. And that's why the standard's written the way they are. They do not want areas being impacted. So these are being designed to have more fault ride-through capability, what's called, to hang in there. which means you and I have more of a challenge to protect our system from them. So how's that? Well, like I said, a lot of people don't even realize this is happening. And that's kind of one of I told you, my point of this discussion is to open our eyes a little bit. And I'll come back to the discussion point on why, as operators, we've got to be mindful of a few things, because all we can do is work with the hand we're dealt. This is what's happening. I will say, if you have products online that were built during and permitted, they're under the older standards. But anything coming on new is going to be on this new standard. So I hope that answered the question. Does it look like that did, Ashley?
Yes, he said thank you.
Okay. All right, I'll come back to that point because we will talk about that just a little bit more here in a few minutes. Okay, so kind of back to this point then, the coordination example. Like I said, that's a good one that kind of demonstrates the potential that you may have a breaker not doing its job because, and if you think about it intuitively, you've got a local fault feeding source that is going to react very quickly to a fault. And we'll talk about that again in a minute. But it could do it before your breaker device that maybe doesn't have a fast enough trip potential. So how about another example? Let's do the, open your eyes even more. Okay, I refer to these and others do as sympathetic and nuisance trip examples. So let's look at my figure A. And it's kind of the same example. They just kind of refer to it two ways. But if you look at figure A here, you got the substation and the bus, breaker B. So normal fault current B, or in blue, feeding into that fault would normally operate breaker B. But what can happen is in an adjacent either feed or in example B, it's kind of the same thing within the feeder versus being at the substation bus level. But the point is the same, whether it's sympathetic or a nuisance operation, is your PV behind its own reclosing device could cause an operation on an adjacent feed breaker trying to feed over the bus work into that other fault on an adjacent way. A lot of people don't realize this example, this potential exists. That if your breaker in front of the PV device, and here's how it typically plays out, and this is what it looks like. If you have to put on a single 200, 500 kW system, the impact is substantial all at once. But here's what also can happen. This is what I call the creep up on you mentality. You put one 10 kW system on, no big deal. But you go down the road and start permitting systems, and pretty soon you look back and say, how many do I have on the system? We got 50. Where are they at? Oh, did you know I have 25 on one feeder? Now, what does that look like, and how does that drive this discussion? And that's what we have found, and I found here at Finley, and we've been doing more consulting work for clients, is evaluating system protection schemes to see where are you, and inadvertently permitting these things in numbers that are starting to get up in magnitude. Do we have this potential? And you may not realize it until, I think that's why I told you my story about the lineman talking about the run-throughs. And you don't want to hear about a story in the breaker and the lineman saying, yeah, tripped the other breaker too. I had twice as many people out, and you won't know it until you look at your safety numbers and realize you're off. And the guys are out fixing it and may or may not bring it to your attention. They may just deal with it because it's business as usual, status quo kind of thing. But this is important. This is why a lot of people, again, tell me afterward, wow, Sean, I didn't know that could happen. Kind of back to my all faults not being created equal. Is that a comment, Ashley? I see it popping up sometimes. No? Okay, I'll keep moving.
Sorry, my comment, or my mute, I'm not quick at the mute. No, there were no new comments in regards to that.
Okay. I'll just try to be responsive if something does come up. I just bring this one up, that the potential for harmonic distortion is there, is a present possibility. It tends to be, I will say, with the newer hardware builds with inverter technology, this has been lessened, which is a good thing. I remember early on permitting some small wind that had an inverter that I was getting some harmonic impact. And I had to, at one point, had to require harmonic filtration on a customer in order to mitigate some of this. It was impacting the neighbor and having some impact. I bring that up that we should be checking harmonic impact when you're doing your site testing. But in newer devices are made and have a lot of this, the active regulation is doing a much better job. I just bring it up. Okay, so a couple things or a couple points on how a solar inverter is a little different than a traditional induction fed generation source. And I want to talk about that just for a few minutes. It's really, the difference is how they feed the fault. And that's why it's an impact to our systems. You know, a synchronous generator, if you look at that, you typically have higher fault current magnitudes, and it's longer periods. They tend to be, you know, you got a rotating device, it's ramped up. It can feed in higher magnitude. It's not as quick to respond if you look at it, if you evaluate based on a cycle level. But an inverter, a DG inverter especially with power electronics, they used to be more like 2 to 3 times rated current for magnitude contribution rather than your 7 to 10 times. But the newer inverters sometimes are limited to 1.2 to 1.5. I thought that was astounding when I read some literature on the newer hardware revs of these devices. That's amazing, but that brings up another question. How many of you have done distribution analysis and you look at your minimum fault currents because they act like cold load pickup? And we've got to be mindful of how we size our breaker devices because we don't want to do that. Solar inverter DG can act like a minimum fault current imposter. And you don't even, may not be even aware that that potential could exist. It could act like a cold load pickup because it's such a small contribution that we may not be protecting adequately against it. So again, eyes wide open. I just thought this is interesting for those of my engineering brethren. Here we're trying to get so smart with our devices and connectivity, but yet they're bringing some power plants out of mothball state to use them as synchronous condensers to help soak up some of those from renewables and these kinds of generation sources. They're trying to add and handle. I just thought that's an interesting topic to bring up. With that, here we're going back old school to compensate for the fact that we're getting more nonlinear connectivity, and so we need to balance things a bit more. So they're doing this. So I just thought that's interesting. The nerd in me thinks that's interesting. Sorry. All right. Here's the other part of solar inverters that we got to be mindful of, and I kind of alluded to it. It's their speed of impact. Now that we're talking about power electronic thyristor fed device inversion devices, they can react very quickly. They don't need to ramp up. So their impact per cycle is much faster than traditional generation sources. So how quick? I mean, the point is, our traditional schemes really aren't fast enough to handle the fault current contribution that these things can make. If you don't have your smart device set down there with 101, 104 level speeds at your fast trip potential, then you may be missing these things. They may go right through that device and get to a device where it can trip. So if you've been on a feeder, this will ring true. If you have a feeder with a lot of DG impact and you're seeing some trips at your substation where you got your smart breaker and you're downstream, you've missed some, then let's just pay attention kind of thing. So that's my point with that discussion, just recognize it. Okay, the fault right. So let's talk about that point, because this is important. I'm bringing that point back to a head that you were bringing up. So if this helps, and you look at what the reliability councils are doing, that ultimately what I alluded to earlier is the point. They're looking at, yes, we know we've got to protect against faults, but we're looking at large scale reliability. And the system operators for those control areas, they can't have multiple 2 to 10 megawatt systems coming offline at the same time. And if they're all built with, think about that, if they're all built with similar electronic schemes, then potentially they could all be tripping together. And that's why they've been designed to handle what grid operators would call minimum level threshold events. Hang on, so to speak, so that they stay connected and they don't cause cascade effect, is really the point. So that's the point. We're at a little bit of a battle with their impacting majority, and we're trying to deal with our systems at a local level. So we're not going to win the battle. We just have to do a good job of protecting our systems with the technology that we have there. That's likely. I just thought this is interesting. Part of the, if you want to nerd out again on some of this, what's allowing these inverters to do this? This is really, there's some great white papers on it, but it's some interesting bedstand reading. I like that. It's all basically a feedback mechanism that they're able to, that's how they're doing the fault line. In a long story short, they're looking at the vector analysis, even the positive negative sequence coordination to be able to, they're analyzing it at that level to keep these things on. So it's kind of interesting, but the point is that you look at what they're doing. They're trying to minimize sag and the impact, or we're trying to do that, but yet the inverter attempting to maintain that connectivity, unless it's a high magnitude event, it's going to hang on as best it can until we have a voltage fault that takes it off. So I know this has always been a concern with linemen that start asking, hey, Sean, how do I know when I go up to grab that line when it's down at the sub that I'm okay? Well, your inverters should be disconnecting and cutting loose. And the question is, yes, in a voltage fault condition, they should be coming off according to 1547 standard. But in those minimal events, this would be the fast impact stuff, would be the ones that are more impact in this case. But they can feed into the fault. That's really the point of that discussion. And it's based on their design parameters. Each one's different. And the newer ones are going to be able to do a little bit better job of the ride-through capability. And this is the bottom line. This is why I bring it up, and it's kind of really why the thrust is here in the first place, is they weren't, our systems, the way we built them, even if we're starting to get smart distribution breakers, the way with the traditional hydraulic device was not designed to handle a high level impact of these things coming on. Now, maybe if you've got one or two on a feeder, you don't see the impact and you're fine. But you either get scale issues with multiple systems or single larger systems. And the question is, have you analyzed your distribution, your protection schemes to know that they can mitigate the things that we've been talking about? So what do you do about it? Other than, we're going to change every device out. What's this solution? One thing is, at the external level, this is kind of interesting. The system operators, the regional operators, they actually want these things in place. They want external communication schemes. They want anti-islanding control, the ability to, they want these large-scale DG systems to respond to their real-time pricing signals and dispatch, other things. And it's pretty interesting to see the control operators having some metric ability to hang on to them. Obviously, they've got cybersecurity concerns when they can control those from a large-scale area, but that's what they're concerned about. Now, let's take it down to you and I at the distribution level operator. And the point is this: it's not only going to take smarter devices that can mitigate, that are fast enough, that can coordinate better, but it's going to take communication. And that's one of these things, and I have a slide in a second, I'm going to demonstrate why, but again, I talked to a lot more co-ops than I ever did when I was at one. But what I find is most people are content with a low-level, low-bandwidth communication means to do what? SCADA, AMI, the minimums, get into the substation, pulling that data in. A few have some smart device downstream, either doing with the same kind of thing, or some have went all the way and they've went to fiber or other more dedicated fixed wireless and other means with higher bandwidth capacity. Perhaps they're doing broadband. We have a ton of co-ops doing that, of course, and they have a means there. But that level of adoption for communication means typically is a driver for your smart grid adoption, I find. And this is one of the answers for, let's say, like that sympathetic and nuisance tripping example I gave you. The answer is direct transfer trip. And what I mean by that, they've been telling us for a while with manufacturers about how if you had smart devices with controls, you could, and of course the perfect example is to have a radial feed, a loop feed, not a lateral, extended lateral where it doesn't go anywhere. But in those, if you got a loop potential, you can have the devices coordinated and talking to each other in such a way that you can isolate segments, feed from the other, back feed from the other way, and minimize the impact to consumers. So that's perfect, but we all know that distribution feeders don't always look like that. A lot of them are long radials. I had some 20-mile feeders that went nowhere, just went out to one end service. But even on those kind of feeds, when we have sub-devices talking to and coordinating with downstream devices, especially in the impact with DG being mid-feeder, you've got the potential for these devices to talk and coordinate and eliminate that potential for nuisance trip, where they would say, no, I'm taking this fault, you're not, and see how you can segment and coordinate. But until you are at a point where you have two things: one, smart grid adoption, better devices that can do those things, and two, communication means that allows you to have that distribution automation potential, you don't have the way to mitigate. Today, this is the simplest way for us to do that with our systems. Well, so what else, Sean? If that, I can only use so many a year on budget. So what other options? Well, like I kind of gave you some basis. A lot of this, how these DGs impact and what they can do is dependent on their manufacturer and how they're obviously being written for the IEEE standards. And like I mentioned, they've got a lot of the fault right through capability coming in when it comes to the ability to control these. Here's a couple points. I just started thinking about this out loud. Balance of where they're at. Well, how many of us can tell the hog confinement operator that that's not the best place for him to put DG? You need to put it over here. It doesn't work that way, right? They call you and say it's going or X marks the spot. Tell me I can do it. That's pretty much the answer to us is, I want to know when I can put this in, make it work. And as a distribution operator, we've got to not only permit that appropriately, but we've got to make sure our protection scheme is there to protect them and all their neighbors from them and their system installations. So, they say that there's some really neat zero sequence and negative sequence current component detection devices coming that might allow us to do a one-stop better mitigation effort. They're not there yet, and probably pricey anyway. So we don't have that potential for this. So I guess that's my point. I'm right close to where I was wanting to be on time. But my point in all this discussion really truly was, I want to make distribution operators aware and of that potential, and really making them take a second look at their system and their schemes to say, what do we have? And if anything else, survey your DG installations and see if you have a greater than average abundance of those systems starting to congregate on individual sites. So I would open up the questions for you guys. Dan, Ashley, anybody to bring in or anything else that might come up?
I think at this point, Sean, if they want to unmute and ask a question, that would be okay. Otherwise, you're welcome to filter it through the chat box and we can relay it for you.
Hey, Sean.
Yes, hey.
Hey, this is Larry Burns at SIPC.
Yes, how are you?
I'm doing good. How are you?
Good.
I had a question. Are you familiar with 3v0 protection and the requirements for that or the impacts on inverter-based systems to high voltage side voltage increases?
I'm not as privy to. I have not worked with that. Enlighten us, if you would.
Well, I guess I can't go into all the technical details, but the way that I understand it is, let's say you have a substation and you have, let's say, more solar generation than you do loading at the station. And let's say you have a delta to Y transformer.
Okay.
Well, zero frequencies don't pass through a delta to Y transformer. So a high side fault will not be seen by any protection you have on the distribution side. So a high side fault, if one phase, let's say line to ground fault is hit, the distribution side won't see it. And so what you have is the potential for very rapid voltage rises on the transmission side, which potential to exceed your insulation levels of your substation equipment. So years ago, the 3v0 protection, I think, was required, especially for DG that had, let's say, bigger, heavier mass machines.
Yep.
So, but I don't know how inverters respond to it. So we're just concerned that, if we put some large solar units out there and we don't install 3v0 protection, under some cases, we may see some damaged high side equipment, bushings, insulators, things like that. And in our case, high voltage protection or 3v0 protection get pretty expensive. it could make or break a solar unit if we put that investment on them, because it's 69 kV PTs with a relay of some sort there that's going to trip them off quickly for a fault on the transmission side. Now, that doesn't even get into reclosing impacts and all that on the transmission side, but there's some complications, and I've talked to a lot of people about this 3V0 protection, and I've yet to have anybody give me a definitive answer. So I thought I would ask, since you've been working on it lately, and get input.
We haven't had to do it at the, what you're calling we'll call the transmission impact level, because most of my focus has been distribution level, like you're saying. Now, you bring up another point, which is also interesting, because that has come up, which is you get enough, a decent enough size system, and do you have enough capacity to handle the output load, which is a whole other consideration. I've had that more than once. I mean, I ran into it at our co-op when I did our wind back when. I was over capacity in like the spring. In the fall, we had grain drying. And in the spring, when it lightly loaded, we'd exceed the load capacity, and it would backfeed. And that was a really awful situation where I'd be buying it for myself at the next station on the transmission. And so that's a whole nother, you kind of alluded to that. That's a different discussion. We have had to expand some sub areas, or in those areas we can't, we got to come up with metering schemes to mitigate that. So that's just a whole nother one. But when you're saying, here's the only thing I would say to what you're talking about. There's two ways to mitigate. There's obviously, like you're saying, being on the 69 kV level and trying to stop it at that level to try to minimize fault. But the other is to force the unit off quickly. And there are some devices, I mean, I can imagine if you're 69 kV level, everything's going to be expensive. But could there be some, what we're kind of like a direct transfer trip communication methodology, where you would have fault sensing capability at the substation, probably at the transformer, that could then trip a device based on those signals and take it off so it can't contribute? I just wonder if that might be a cheaper way to mitigate.
Yeah, absolutely. That's what we're doing right now in one case. And what we're trying to do is send a trip signal to a distribution feeder in a station to trip off that circuit. And that comes from, the signal comes from our transmission relay. Okay, so it happens to work out well there, but the only reason it works out well is because this generator is on a feeder that's protected, that's by itself and has its own breaker. So you're not affecting other customers. Another thing, it happens to be close to a transmission substation. We happen to have fiber there. So we're going to use the fiber from our relays into the station just to trip that breaker that's under our control. And you can imagine trying to send that trip from us to them. We have to count on them to maintain their equipment, to maintain their controls, and to count on our signal getting to them and their equipment tripping. And once it gets to that point, how well can you trust it? If it's out of your control, I would lean more towards a 3V0 protection to keep it in my control if I didn't have an option. But at this point, I don't know if it's needed, and I have a hard time putting $100,000+ burden on a solar installation. But I also have a hard time putting the possible ramifications of that on our members if there are failures or things that come from that solar unit down the road. Yep,
you're only going to need one event to justify paying for that thing, and impact and the political fallout and everything else. We all know how that works. But your point brings up a good point, that many that are trying to get by with either direct transfer script or schemes and other using a wireless methodology may not have the low latency needed to be as fast as what you're talking about. What you would need would be, that would have to be so sub-cycle in its impact. You'd almost have to have fiber, I would think.
And you definitely want it in your control and not on some other communications medium like cellular or whatnot. You just can't. To me, you can't depend on it for the speed we're talking about. But anyway, it's a whole nother discussion. I just thought I would ask you about it, but I appreciate your thought and input.
I very much appreciate bringing that up. That's a great one. I hasn't come up with a client, which is good. I mean, but I'd be happy to help off grid if you wanted me to look at it with you, right? That's very intriguing to me from the engineering side. But I would say that not only the fiber connectivity and other, But one thing I'll bring up on that, you're talking about comparing the scheme where you can protect at the transmission level versus something like this and that doing fiber. What I find though is many people will, since that one is a one and done dedicated protection, but yes, it does its job. When it comes to communication, distribution, automation, and other, you might be able to justify that expense by doing other things with it. We do find that potential where if you're going to run fiber, now I can do boom, 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 and I can eat that cake a couple different ways after I spent money on it. So that's the one thing I would add there versus if you do the 3V, that protection scheme, it's just for that point, that's all it does. And I very much appreciate that, bringing that up, especially for this audience. That's very instructive for us.
Yeah, all right. Thank you. I'll probably shoot you an email sometime on it.
Do so. Happy to discuss further.
Yep.
Anything else for the good of the cause and our ability to learn something?
Sean, I had one that come through chat. What do you see as solutions for voltage regulation issues created by large amounts of distributed generation being interconnected on a long rural feeder? Yeah,
that's a great one, and that's why I demonstrated that point. One thing that's got to happen is obviously we got substation regulation, and a lot of people just have line drop compensation dialed in based on the parameter of, well, let me be honest. How many of you have the line drop in there that's been in there for so long that that's just the way you do it and nobody's touched it in a long time? And that's what I typically find is sometimes more of the impact. You might find that just it's not tuned properly for the feeder anyway. But two things. One, midstream regulation may be required in order to keep things more in check. I mean, if you're kind of doing buck boost, depending on where the PV's injecting. So it may, that's, you're talking about as a distribution operator, what am I going to do about it? You may have to add midstream regulation that can, let the downstream coordinate with the substation by being maybe faster or slower response one way or the other, depending on where your source is. But you're also going to have to look at the line drop compensation, the way they're set. Maybe you have nothing in yours, but you may need it. And it depends on how you tune the feeder to do so. So that's kind of in a nutshell. The quick way, every scenario is a little different. Depends on where the injection is. If you've got a bunch of little ones, it may be enough just to add midstream regulation, let them coordinate, and keep things fluid that way. But yeah, that's a great point. It's just keeping status quo is the problem, is where people typically see the issues.
Another one, Sean, it says, Sean, do you see many co-ops or utilities utilizing meter data, i.e. minimum max voltage on the meter, then processing it through a report writer to look for grid norms?
Yeah, that's a great one. And for anything that becomes steady state, we all know the meter is not going to give us faster responses when your distribution automation, end of line voltage points are off a regulator where you can pull it and get it. For some of you though, some of the systems probably do have some fairly fast voltage data, but most definitely, I always refer to those things as poor man's SCADA, the best term I can come up with, methodology for trying to do that, but by all means, yeah, getting your feedback. I mean, look at how the distributed generation people that are designing their devices build those inverter systems. They build them with feedback loops. If you can do that, the better thing will be to have some way to mine your MDM to pull that to where you're not having to always go looking for it. That's the challenge, is do you have any intelligence where you could be looking for and giving yourself notification alerts off that? That's what you don't have with pulling out of MDM versus SCADA, where you've got it real time and you can use it to do calculations. Most definitely. Say if you've got it, you already spent money on it, use the poor man's SCADA system, what I call, to do what you can do. For sure. Anything else?
Okay, well, if there aren't any other questions, I just want to take a moment to thank you so much, Sean, for joining us today and for doing this presentation. You were our first webinar of the AIEC webinar week, so thank you so much for that. For those on the call, We have the next one coming at 10:30. It's smartphone apps to replace paper for utility work. If you're not registered for that and you would like to attend, please shoot me an email. I can get you that information. Thank you all so much for joining us. We have many weeks left of this, so be looking for information on that. And again, thank you so much, Sean, for taking the time to be with us today.
Welcome.